Okay, I'm a pre-T trainee, so I'm sorry if I sound like a girl or a 12-year-old boy. The remake of this after I am old enough to get on T will be legendary, dude. Anyway, the most of Earth's history from the formation of the Earth 4.6 billion years ago to approximately 541 million years ago is known as the Precambrian time. The rocks of this age are found in the northern Yellowstone and in the hearts of the nearby Teton-Beartooth Wind River and Groves Ventura mountain ranges. During the Precambrian and the subsequent Paleozoic and Mosaic eras, 541 to 66 million years ago, the western United States was covered at times by oceans, sand dunes, tidal flats, and vast plains. From the end of the Mosaic through the early Cenozoic and the mountain building processes formed the Rocky Mountains. During the Cenozoic era, approximately the last 66 million years of Earth's history, widespread mountain building, volcanism, faulting, and glaciation sculpted the Yellowstone area. The Absaroka Range along the park's north and east sides was formed by numerous volcanic eruptions about 50 million years ago. This period of volcanism is not related to the present Yellowstone volcano. Approximately 30 million years ago, the vast expanses of today's West began stretching apart on the east-west axis. This ongoing stretching process increased about 7 million years ago and created the modern basin and range topography, north-south mountain ranges with long north-south valleys, which characterizes much of the West, including the Yellowstone area. About 16.5 million years ago, an intense period of volcanism initiated near the borders of present-day Nevada, Oregon, and Idaho. Subsequent volcanic eruptions can be traced across southern Idaho towards Yellowstone. This 500-mile of more than 10 calderas was created as the North American plate moved in a southwestern direction over a shallow body of magma. About 2.1 million years ago, the movement of the North American plate brought the Yellowstone area closer to the shallow magma body. This volcanism remains a driving force in the Yellowstone today. Magma hotspots and the Yellowstone supervolcano. Magma, molten rock from below the Earth's crust, is close to the surface in the greater Yellowstone area. This shallow body of magma is caused by heat convection in the mantle. Plumes of magma rise through the mantle, melting rocks in the crust, and creating magma reservoirs of partially molten, partially solid rock. Mantle plumes transport heat from deep in the mantle to the crust and create what we call hotspot volcanism. Hotspots leave a trail of volcanic activity as tectonic plates drift over them. I skipped the line. Sorry, man. Skipped the line. As the North American plate drifted westward over the last 16.5 million years, the hotspot that now resides under the greater Yellowstone area left a swath of volcanic deposits across Idaho, Snake River Plain. Heat from the mantle plume has melted rocks in the crust and created two magma chambers of partially molten, partially solid rock near Yellowstone surface. I said surface. Why did I say surface? Heat from the shallowest magma chamber caused an area of the crust above it to expand and rise. Stress on the overlying crust resulted in increased earthquake activity, along with new formed faults. Eventually, these faults reached the magma chamber, and the magma oozed through the cracks. Escaping magma released pressure within the chamber, which also allowed volcanic gases to escape and expand explosively in a massive volcano eruption. The eruption spewed copious volcanic ash and gas into the atmosphere that produced vast, super hot debris flows, pyroclastic flows, over the existing landscape. As the underground magma chamber emptied, the ground above it collapsed and created the first of Yellowstone's 3 calderas. This eruption, 2.1 million years ago, along with the largest volcanic eruptions known to man, coated 5,790 miles of ash as far away as Missouri. The total volcanic material ejected is estimated to have been 6,000 times the volume of material ejected during the 1980 eruption of Mount St. Helens, Washington. Is it St. No, it's Mount Street, isn't it? Whatever. Anyway, a second significant, though smaller, volcano eruption occurred within the western edge of the first caldera approximately 1.3 million years ago. The third and most recent massive volcanic eruption, that's a big number, 631,000 years ago, created the present 30 by, wait, would that be, I don't think I read that right. I think it's 6 million and something years ago. I don't know, I'm just gonna continue reading it. Created by the present 30 by 45 mile wide Yellowstone caldera. Since then, 80 smaller eruptions have occurred. Approximately, that's a big number. I'm just gonna let y'all look at it. I'm not even gonna try to read it. I'm done with trying to read big numbers. One of these created what is now the west thumb of Yellowstone Lake. During and after these explosions, eruptions, huge lava flows of viscous rhyolitic, I think, lava and less voluminous basalt lava flows partially filled the caldera floor and surrounding terrain. The youngest of these lava flows is the 70,000-year-old pitchstone rhyolite flow in the southwest corner of Yellowstone National Park. Since the last of 3 caldera-forming eruptions, the pressure from the shallow magma body formed 2 resurgent domes inside the Yellowstone caldera. Magma may be as little as 3 to 8 miles beneath. Sour Creek Dome and Sour Creek Dome and 8 to 12 miles beneath the Malley Lake Dome. And both domes inflate and subside as the volume of the magma or hydrothermal fluids changes beneath them. The entire caldera floor lifts up or subsides too, but not as much as the 2 domes. In the past century, the net inflation has tilted the caldera floor towards the south. As a result, Yellowstone's lake southern shores have been subsided and now trees stand in the water. And the north end of the lake has risen into a sandy beach at Fishing Bridge. recent activity. Remarkable ground deformation has been documented along the central axis of the caldera between Old Faithful and White Lake in the Pelican Valley of historic time. Why can I can't speak today. Surveys of suspected ground deformation began in the 1970s. I can't speak today. Suspected ground deformation began in 1975 using vertical motion surveys as benchmarks in the ground. By 1985, the surveys documented unprecedented uplift of the entire caldera in axis of a meter, 3 feet. Later GPS measurements revealed that the caldera went into an episode of subsidence, sinking until 2005, when the caldera returned to an episode of extreme uplift. The largest vertical movement was recorded at the White Lake GPS station inside the caldera's eastern rim, where the total uplift from 2004 to 2010 was about 27 meters, 10.6 inches. The rate of rise slowed in 2008, and the caldera began to subside again during the first half of 2010. The uplift is believed to be caused by a movement of I can't speak today. I'm having issues. Caused by the movement of deep hydrothermal fluids or molten rock into the shallow crustal magma system at a depth of about 10 kilometers beneath the surface. A caldera may undergo episodes of uplift and subsidence for thousands of years without erupting. Notably, changes in uplift and subsidence have been correlated with increases of earthquake activity, lateral discharge of these fluids away from the caldera, and the accompanying earthquakes. Subsidence and uplift relieves pressure and could act as a natural pressure release valve, balancing the magma recharge and keeping Yellowstone safe from volcanic eruptions. Future volcanic activity. Will Yellowstone's volcano erupt again over the next thousands to millions of years? Probably in the next few hundred years, not likely. Most activity would be lava flows, such as those that occurred after the last major eruption. Lava flow would ooze slowly over months and years, allowing plenty of time for the park managers to evaluate the situation and protect people. No scientific evidence indicates that such a lava flow will occur soon. To monitor volcanic and seismic activity in the Yellowstone area, the Yellowstone Volcano Observatory was established in 2001. YVO is a partnership of scientists from the U.S. Geological Survey, National Park Service, University of Utah, University of Wyoming, University Navistar Consortium, and the State of Geological Surveys of Wyoming, Montana, and Ohio. It's Idaho, not Ohio. Did I drink the wrong Frosty Freeze this morning or something? Anyway, YVO scientists monitor Yellowstone volcano with a real-time and near-real-time monitoring network of 26 seismic stations, 16 GPS receivers, and 11 stream gauging stations. Scientists also collect information on temperature, chemistry, and gas concentrations at selected hydrothermal features and chloride concentrations in major rivers. Monthly activity summary, real-time monitoring of seismicity and water flow, and near real-time monitoring of ground deformation can be found at the Yellowstone Volcanic Observatory website.